Good morning. Today we'll study the topic of variational inference or variational Bayes. So let us go back to the original Bayesian inferencing problem that we studied earlier. So the idea is that you have a set of observables or latent variables or whatever, a set of variables which we call x, and a set of parameters of the model which we call theta. So the Bayes rule says that the posterior probability p theta given x is proportional to p x given theta into p theta. There is a constant, proportionality constant. So this basically means that if you are given a set of observations, the training set x, you have to obtain an estimate of theta, but not just a single estimate of theta, but a distribution on different probable values of theta. And we find that what basically happens is that you have an assumption about the prior. You have an assumption about the prior distribution. What are the different probabilities of various values of theta? And then you multiply it by the likelihood that comes from the data. So assuming this to be the parameter value, what is the probability of explaining x? So this is the likelihood. So you have the likelihood, and this likelihood kind of modifies the prior. Okay, it concentrates the prior to the region where you have data, or depending on what the data distribution is. So you get, and after this multiplication, you get your posterior. So the role of prior is more like, so if you just take data, it would be some likelihood function. And this may be not very robust. This may be containing noise of the data. This may be due to small size of the sample. This may be not entirely correct. The role of prior is to kind of condition or regularize it. That means it kind of protects against the noise to some extent. So the prior, even though we mentioned it's a previous knowledge, this prior is basically some kind of a constraint, some kind of a smoothness condition or a broad constraint or something. It's rarely we have exact knowledge of the what the prior should be. The prior is usually some kind of a broad knowledge we have about theta, usually taking the form of some kind of smoothness constraint or something. Its role mainly is to protect against noise in the likelihood, or kind of help you when your likelihood estimate is not good because of less data. But the thing is that usually both the prior distribution, the functional form of the prior distribution, and also the functional form of the likelihood distribution are user choices. The user, so say either I choose a Gaussian or a gamma distribution or a beta distribution or a Bernoulli distribution, whatever. It is a user choice, and this is just an assumption that the reality matches with this choice, but which is only an assumption. Okay. So usually we make the assumption, but the point is that it is a different matter whether the assumption is correct or wrong, but there are some computational aspects involved with the assumption. So usually our assumptions are derived by two considerations. One is how close it is to the reality. Second is how much tractable or computationally feasible it is. So usually we choose Gaussian because a lot of mathematics and derivations becomes easier if we assume it to be Gaussian. Also, Gaussians are very well reflecting nature. Okay, so these are driven by these two considerations. So usually this p likelihood px given theta and p theta, these are known and these are choices. But moment you multiply them, things may get complicated, computational. Okay, so now what I do is that I remove the proportionality and I actually bring in the constant. So as you know, by Bayes rule, P of theta given x equal to P of x given theta into P theta by Px. So this is the likelihood. This comes from the data. P theta is the belief, the prior knowledge. And the denominator Px is the so-called evidence. Its name is evidence, Px. So if you want to get not just a proportionality, but the actual distribution P theta x, you need this denominator. And this denominator is kind of a normalizing constant. It's kind of a normalizing constant. Okay, it ensures that P theta given x is a distribution. But this Px, this denominator evidence, is calculated by an integration. So this quantity Px given theta into P theta, this is basically the joint distribution of Px comma theta. This is the joint distribution of Px comma theta. And we marginalize out this joint distribution with respect to theta and to get Px. So marginalizing means we add up over all possible values and kind of aggregate over all possible values of theta so that we get a value of marginal with respect to x only. Okay. And so even though Px given theta and P theta may be simple or assumed or known, this integration may be computationally difficult. It might be difficult to form a closed form expression for this. Okay. Also, I mean, you may ask that, okay, in why do I bother about a closed form expression? We are actually dealing with data points. So if we take just data points, this would be replaced, this integration would be replaced by a summation over all the training set examples. And if you really have big data, then this summation would be computationally intractable. It would take a lot of time. Okay, so the situation is slightly better if the prior and the posterior are conjugates. That means the functional form of the prior is the functional form of the posterior turns out to be the same as that of the prior. So, for example, if the prior is a Gaussian, posterior is also Gaussian. So, what we call as conjugate priors. But such then of course then this is a closed form. Then it can be shown that it becomes a closed form expression, and things are easier to compute. But that is often not the case. You don't have conjugate priors, so there is a intractability in computing this denominator, the evidence, and without which you cannot compute the full posterior. So people have proposed since, I guess, 1990s, people have proposed that is it possible, instead of computing the exact posterior, instead of exactly knowing the distribution of theta given x, can I have an approximate posterior in less computational time? Okay, so this gives rise to a set of algorithms known as approximate Bayes algorithms. I think one of the example you have all seen is that, note that if you look at this, suppose I want to find theta maximum a posteriori. That means I want to find that particular theta star which maximizes this posterior variability among all theta. Note that the denominator is independent of theta, so the maximum wouldn't change if we ignore the denominator. And the denominator is what is difficult to compute. So even if we don't compute it, the map doesn't change. So computing the map, computing the full posterior is difficult. Computing the map is actually not so difficult if we know x given the likelihood and the belief and the prior, if we know that. And often these are simple. These are assumed to be simple. The moment you do this integration, it becomes complicated. So one crude approximation is that, so suppose this is your full posterior distribution. You have estimated the map without computing the evidence. you approximate it by a delta kind of distribution where the entire probability mass is concentrated only at the map value, only at theta map. So it's a spike at theta map and zero everywhere else. So that's a very crude approximation to the posterior distribution. This we have already done, but this is not very useful in most situations. We also have seen a Laplace approximation. That means we have approximated the posterior by doing its Taylor series expansion and taking the first two terms. So you know the functional form of the posterior. You replace the integration by a Taylor series and take the first two terms. That's the Laplace approximation. That is also not so easy for many situations. So two of the useful, or rather popular techniques for approximate inferencing is the first one is something known as variational inferencing. We'll soon see what it means. And the other is it's kind of numerical. That means instead of computing the full posterior, you sample out of the posterior, which is easier to do, and then construct the full posterior based on the samples. So you sample out. So all these Markov chain, Monte Carlo, Gibbs sampling, Metropolis Hastings, they are under this sampling based category. We'll come to that later. But first, let us go ahead with the Laplace approximation. The variational inferencing. Okay. So the idea is as follows. Let this big ellipse be the set of all possible distributions. And so it's a set of all distributions. And this p theta given x, the posterior, is one point in this set, which is difficult to compute. But we have a set of distributions which we call Q, a set of distributions which we call script Q. We name them as variational distributions, which are more tractable, which are simpler, which are easier to compute. We'll let us see what it means exactly by easier to compute. Basically, the integration should be easier to done. So we have a set of this smaller ellipse is the set of all distributions Q theta rather, which are which we call them as which is a more nice set, which is a more tractable set. And note that this is a set of distributions. So any one distribution among them I call as Q. It is a distribution on theta. Note that this is also a distribution on P. Sorry, the P is also a distribution on theta. Since P is difficult to compute, what we do is we try to approximate P using one of the Q belonging to this set, script Q. Why one of the Q? Because Q is a better set to compute. So I want to approximate it using this. It's like if you have a complex curve, I am approximated by a straight line because the straight line is easy. And this is called a variational distribution because this Q is basically a family of distributions which can vary over this set, script Q. Okay. So the thing is that now the approximation problem is basically an optimization problem. The problem is the best approximation of p theta x in terms of Q is nothing but the closest point in this set Q, call it Q star theta, to p theta given x, to the posterior. The closest point in this set to this posterior. So my optimization problem is you vary Q till you get Q star, which is closest to P the posterior. And that instead of using P theta given x, instead of computing P theta given x, we will compute Q star theta and use that. If it is a good approximation, that will not create a lot of problem. Okay, so notice carefully that the this optimization problem is little bit complex, because this p theta x, even though I have shown it as a point, it is actually a function. It is a density probability function over theta. It is a function over theta. And any q theta inside this ellipse, inside script q, is also a function. So our optimal solution is not a single, not a point. It's a function. It's a function. So basically, among all functions which belong to this category, find one function q star theta which is closest to this function p theta given x. Such optimization problems are called variational problems. In normal optimization problems, you have an objective function, you have a x which determines the objective function, you find x star which maximizes the objective function. Here, the x is not a point, not a vector, it's a function. And what is the objective function? What are we optimizing? We are optimizing the distance of this q function to this p theta function. So it is as if every function q here can be characterized by a scalar value, which is nothing but its distance to p theta given x. Every function here can be characterized by that, a scalar value. This scalar value is called a functional. It's a property of a function. So functionals are scalar value which tells something about a function. For example, the energy of the function, the area under the curve of that function, that's a functional. Okay, or the highest point of the function, that is a functional. The average value of the function, that is a functional. So here the functional is nothing but the distance of each function. How we measure distance, I'll talk later. Distance of each function to p theta given x. That's the functional. That's the goodness of every function. And with respect to this functional, we need to find q star, that particular q which minimizes this functional. So this is an variational optimization problem. It is usually solved using something called a variational calculus, but I'm not going to it. I'm in the general form. I'll just discuss the special form useful for us. Okay, in general, these are numerically very difficult problems to solve. In fact, there is no general solution for this. We'll talk about a numerical solution for a special type of cube. Okay, so the next is how do we measure this distance? How do we measure this distance? So, as I have told, p theta given x is a distribution. Q theta is also a distribution. So we need some distance between two distributions, and we use the Coolback-Leibler divergence. It's the measure of closeness. It's not a distance exactly, but it is a measure of closeness between two distributions. So I have mentioned before, just let me repeat again. So the Coolback-Leibler distance between two distributions q and p is nothing but the integration. In the finite case, this can as well be the summation. Integration qx into log of qx by px dx. Log of qx by px into dx weighted by qx. So this log of qx by ps is nothing but the log likelihood ratio between qx and px. You weight it by the qx. If you remember the definition of expectation of a random variable, so it's integral qx into x by qx into x. That's the 1 by integral qx, which is 1. So the expectation, this can be thought of as the expectation of the log likelihood ratio. Log likelihood. So this is the likelihood ratio. Qx in qx by px is the log likelihood ratio. This is Coolback-Leibler distance is nothing. This integration is the expectation of this log likelihood ratio. You remember the expectation of any function. So the expectation of any function with respect to some probability distribution t over some variable x is nothing but integral dx, which is the probability value, fx dx over the entire domain of x, or rather sometimes called the support of x, where this dx is non-zero. Okay, so this is the definition. So here we replace d by qx, q theta rather, and fx by log of q theta by p theta. Okay, so this Coolback distance is nothing but the expectation of this log likelihood. We have already studied it before. So this we use as our distance in this method, this distance. There are some properties. First is that you can define, or you can use Coolback if both Q and P should have the same domain or same support. And by Jensen inequality, we have already shown earlier that Coolback is always greater than or equal to 0. The lowest value it can have is 0. And the lowest value happens when Q and P are same everywhere where dx is, or rather qx is non-zero. Anywhere, so almost everywhere. So Q and P are equal. And this is not a distance measure because this is not symmetric. There is a directionality. So you exchange Q and P, the expression doesn't remain the same. So there is a directionality. That's why I have put this arrow in this direction. It's not a bidirectional line. And most importantly, this is a very good measure. You can use other measures. You can use Wasserstein distance. There are many other measures between two distributions, but this actually works very well. So this we'll use as our distance measure. So if we use that our distance measure, our optimization problem, known as the variational inference problem, becomes the following. You vary q over all q, script q theta over all script q, and find that particular q which minimizes the KL divergence between q and the posterior, p theta given x, which minimizes this. Okay, so this is my optimization problem. If I solve this, I'll get q star as my best approximation of p theta given x. Okay, but it's a bit difficult to solve this optimization problem per se, because we say that we minimize this distance, but this p theta x, we have said before that it is intractable. It's not difficult to compute. So how do you, we don't know p theta x what it is, how do you compute the KL divergence between q and p? Okay, how do you do that? It turns out by using some simple algebra, we can transform this optimization problem into another problem known as a variational problem, where instead of Coolback between q and p theta given x, we get an expression. In terms of the likelihood and the prior, not the posterior. This is with respect to the posterior. We get another objective function in an optimization problem, which is dependent on the likelihood and the prior, which we know, which are tractable. The intractability is only because of the denominator, the evidence. Okay, so if we can somehow trick out or remove or kind of eliminate the normalizing denominator, which we call the evidence, then there is absolute, and we have an objective function which can be computed using px given theta, the likelihood and the prior, then things are easier. Then, because these are assumed, and if they are assumed, they are known. Okay, we are not computing it. We are computing prior by simple operation, by multiplying and integrating. But that simple operation is not so simple for many cases. So, but if we can remove the denominator, that normalizing denominator called evidence, then we have only these two, which are known, which are easy, which can be solved. Okay, so we have optimization problem which is more tractable. Not something, this is kind of an abstract optimization problem which you cannot solve, but we will transform it into a real optimization problem which you can solve. Right, abstract because this p theta given x is unknown or not computable. Okay, so let us see. The problem is with this evidence. Let us try to expand the evidence. Okay, so px is the so this is we are interested in log of px. So what we can do is that we can sort of introduce. See. Let us look at this expression. So this expression is q theta into log of px into d theta integrated over all of theta. This log of px is constant with respect to theta. So I can as well bring it out of the integration. I can bring it out of the integration. If I can bring it out of the integration, so this basically becomes log of px integral q theta d theta over theta, and q is a distribution, so this thing is basically 1. So all I am doing is that multiplying log of px by 1, so which is log of px. So that's what establishes this equality. This is equal to this. Okay, so now replace log of px by the definition of the conditional probability. Replace log of px. Yes. Replace log of px by this quantity. Okay, because p of theta given x is p of joint distribution by px. Okay, so I can replace px by this quantity. All right, then let us multiply this inside this log for this numerator denominator by q theta. Okay, and then log of ab equal to log a plus log b. So I sort of split out this thing into, so this thing can be written as p of x comma theta by q theta given x into q theta by p of theta given x. Okay, so this let me see. So I write this as this into this. So log of a into b, which is log a plus log b. So I split this up. Note this quantity. This quantity is nothing but the Coolback distance between q theta and p theta given x. Is the Coolback distance. Okay, between q theta and p by the definition of Coolback distance. And this quantity, you may kind of think it of like minus Coolback distance between q theta and px theta. Okay, it's kind of a reverse of that, but this is not exactly Coolback distance. First of all, because we cannot compute Coolback between q theta given x and px theta, because the domain of p is x as well as theta, whereas domain of q theta given x is only theta. So these two ratio, they are of different domain, so there is actually no point in there. You cannot define a Coolback in them. So this quantity is not the Coolback distance, whereas the second term is the Coolback distance. This first term I denote it by, so you note that after this integration with respect to, I can note this thing as see, px theta is known. We'll soon see px comma theta is known. So this is a function of only q. Okay, px comma theta is kind of constant. It's given. Okay, so this is a function of q, and this we call as scriptal. So it's the evidence log of the evidence log of px is the scriptal plus scale divergence between q theta and p theta given x. This scale divergence is that distance we are talking of. Is the distance we are talking of. Okay, so it is that distance plus some scriptal. Okay, if we add up these two, you get the evidence. All right. Now, both these quantities are important. Let us.
Sir,
Huh?
the first term in the denominator, is it q theta or q theta given x?
It will be q theta. I made a mistake.
Okay.
It will be q theta. Yeah, this I think it easily follows from this. I made an error in this. Okay, so as we have said before, that Coolback-Leibler is 0 or positive, is greater than equal to 0. So this first term is kind of a lower bound on log of px, because log of px is this first term plus some positive quantity. Okay, so that means this scriptal will always be less than log of px. Will always be less than log of px. Okay, so log of px will always be greater than equal to this lower bound, because the second term is always greater than equal to 0. Is always greater than equal to 0. Okay, so this scriptal is called a evidence. It's a lower bound on the evidence px. It's called the evidence lower bound or elbow. Evidence lower bound or elbow. This is an important quantity. It's called the evidence. I think you sound a similarity in the EM also. We are trying to replace the, lower bound the posterior by some maximizing that kind of thing. So this is a similar in a more general form. It is a lower bound on the evidence. In the EM, we are not looking at the evidence. We are looking at something else. So this is a lower bound of the evidence. It's called the elbow. Note one thing, that if you did not have any restriction on this Q, if you did not have any, if this Q can be anything, rather it can be entire set, then this distance becomes, the smallest value that distance can take is 0, because then Q is the entire thing. Okay, so basically P also is part of Q, so this can become 0, and then this elbow is equal to 0. This is not an inequality, this is an equality in that case. And Q equal to P theta x. Q is exactly same as there is no approximate inference Bayes anymore. It is exact Bayes. If your Q was the entire set. If your Q is all possible distributions, then it is no longer approximate inference, it is exact inference. Q is exactly equal to P of the posterior, exactly equal to the posterior. Right. In that case, the lower bound is 0. In the lower bound is 0, and this is sorry, the lower bound is not 0. The gap is 0. This evidence is nothing but equal to this lower bound. KL is 0. Evidence is equal to log of evidence is equal to the lower bound. Okay, yeah, but we cannot make Q to be the entire set of distributions, because the entire set of distribution has many intractable distributions which we don't want to deal with. We want to deal with only nice distributions Q, which is a subset of the entire set of distributions. Okay, so this you keep in mind, that basically log of px is greater than equal to some scriptal, which is a function of Q theta. And this scriptal is called the elbow. So I summarize again. So if I just don't write it as a lower bound, if I expand the evidence, log of px is this lower bound elbow plus the KLD which you are trying to minimize, this KLD, which you are trying to minimize. Okay. All right. Now see, this px, log of px is independent of q. So see, no, remember again, the minimization is over all values of q in q, capital Q. Is over all values of q in script q. Okay, but log of px is independent of q. So log of px is kind of a constant in this optimization problem. So in this optimization problem, this is kind of a constant. It doesn't depend on q. Okay, so this plus this is equal to a constant in the optimization problem. So minimizing this quantity, if their sum is a constant, minimizing, and each of them are positive. The minimizing, no, sorry, not with the other statement. I have to check if they're positive. But since their sum is constant, minimizing the KL divergence, that is this problem, is equivalent to maximizing the lower bound, maximizing the elbow, because their sum is constant. Okay, so the value of Q, which will give you the minimum value of the KL divergence, will correspond to the maximum value of the elbow. So I transform this original optimization problem into this equivalent problem. Okay, this is the variational problem. We just instead of minimizing the KL divergence, you maximize the elbow. I think if you remember what we did in EM, it will strike a deal. Similar things are being done. Okay, so this is the second problem, is the one which you are now interested in. Let us look at it into more detail. Okay, so let us we have to maximize this elbow. Let us look at the definition of elbow. So this is the definition of elbow. This is the definition of elbow. I have rewritten it here. This is the, sorry, again I made a problem. This should not be there. This I mistyped in LaTeX. This is the definition of elbow. So elbow is q theta log of p, the joint distribution between x and theta divided by q theta. All right. So let us expand this joint distribution into p of x given theta into p theta. This again will be not there. This again will be not there. Okay, let us expand p joint distribution px comma theta into p of x given theta into p theta. All right. So now this is again a product of two parts. This part by this part into this part. Okay, so I expand the log again. So if I expand the log, it is integral q theta log of p x given theta into d theta plus integral q theta log of, I missed this part too, log of p theta by q theta. Log of p theta by q theta. Right. Now look at this part. This part is nothing but the KL divergence between q and p theta. Remember, we have to maximize this. Okay, so this is the KL divergence between q theta and p theta. In fact, negative of the KL divergence between q theta and p theta, because q theta should be in the numerator and p theta should be in the denominator, and we just put a minus sign, it will get reversed. So it is the KL divergence between q theta and p theta, minus of that. And what is this? This is kind of the expectation of the likelihood Ex given theta with respect to the distribution q theta. Expectation taken with respect to the distribution q theta and log of px given theta. So this is the expectation with respect to q theta, this quantity, log of px given theta. So the elbow which you are trying to maximize is expectation of the likelihood minus KL divergence between q theta and the prior p theta. This is the term. This entire thing is what will maximize. Note that we have done away with the evidence px. We have only the likelihood, which we have assumed is easier, not tractable. No, sorry, not intractable, and the prior, which again we have assumed and it is not intractable. Right. So we only have this likelihood and the prior. We don't have the full posterior. We don't have the normalizing denominator evidence, who's just creating the problem. Okay, and these two are actually known and easy. So this entire expression of elbow is computable, is maximizable rather. It's computable. Okay, now let us look at what this means, what this expression of. So this is an easier problem. Because px, the evidence, or rather p theta given x, is not involved. Okay, so now let us look at this expression in a better way. All right. So this first is the expectation of the log likelihood, which comes from the data actually, because it is px given theta. It's the log likelihood with respect to q theta. So can you tell for which value of q theta this log likelihood, expectation of this log likelihood will be maximized? So let us look at it like this. So suppose this is my log likelihood function. Okay, this is the log likelihood function, and I have another distribution which can be anything. I can vary my q, so at what value of q this expectation will be highest. The expectation, what is expectation, is q into log likelihood, q into log of px given theta summed up over all possible values of x. So you see, if we make q such that the entire q is concentrated at the highest point of the log likelihood, the entire q is like, then this expectation will be highest, because it is the entire density, which will entire mass rather, which will be equal to 1 actually if you sum up, is at the highest point of the log likelihood and 0 at everywhere else. Okay, so any other q you take, it will give some weight to the highest point and some weight to the next other not highest points and so on. So he'll lose some expectation. But if all the probability mass of q, was concentrated at the highest point of this log likelihood, equivalent to the highest point of log of the likelihood itself, px given theta, then you'd get the highest expectation. Okay, and what is this highest point of likelihood, highest point of px given theta? It is nothing but the maximum likelihood estimate of theta. It is nothing but the maximum likelihood estimate of theta, MLE estimate of theta. Okay, so the first term is determined by the likelihood, rather the log likelihood. It's determined by the MLE. And you see, the prior doesn't play any role here. It is only determined by how well you explain your given data. Okay, one thing I forgot to mention. So this x is actually, there will be a further summation. This is for a single x. So if we take our capital X, which is x1 to xn, this log would be summation over 1 to n of this quantity. If we assume x1 to xn as IID. Okay, so the first term of this elbow depends on the data you get. How well theta explains your given data. So it's a data term. Whereas the second term, when is the second term? So we want to maximize elbow. So you'd rather like there is a negative here, and this KL is always positive. So you'd like to minimize this quantity, and the quantity is minimum. Sorry, this should be minimized. Okay, if you take the minus, it is maximized, but otherwise this is minimized. So this one is this quantity minimum when KLD is 0. That's the minimum value of KLD. And when KLD is 0, when the Q theta equals the prior distribution P theta. When Q theta is exactly equal to the prior distribution Q theta. Okay, so so now you are changing Q. On one hand, you want to make Q a delta function concentrated at MLE of Px given theta for the first term. You want to do that. So in order to maximize L at the elbow, you want one hand you want Q to be such a distribution which is concentrated at MLE. So one hand you need Q to be concentrated at MLE. And on the other hand, you want Q to be same as the prior. To be same as the prior because of the second term. But we are not doing any of them. We are rather adding them up. So you want Q to be something which is somewhere in between the prior and the data. Prior is kind of, as I said in the beginning, that prior is kind of a smoothing function. It's kind of regularizer, so to say, in machine learning. Those who know the term, it's kind of smoothness constant. It's a regularizer. It's a belief. Okay, if we had only the first term, your Q would be the approximator of the posterior would be just the MLE. But prior holds you back from that. It gives you a constant. It regularizes you. It holds you back. And it tries to bring it closer to the prior itself. Make Q same as the prior itself. And so there is a combination of these two effects going on when we maximize the elbow. When we maximize the combination, which again makes sense from our previous understanding of what goes on in Bayesian estimate. This makes sense. Right. So as a summary, we would like to our variational inference problem means finding an approximation of the full posterior, because the full posterior is computationally intractable. And we say that the approximation I call as Q. We get the best approximation Q star by solving a variational optimization problem by changing the whole function Q, which maximizes the elbow, the evidence lower bound, given by this expression, which is a combination of the likelihood and the prior, given by this. So this is the expression, or this is the elbow, which you want to maximize by varying Q over script Q. Okay. So now we have got the objective function. We have got the domain of Q where it should vary. Now we need an algorithm to maximize this objective function. Obviously, this is an iterative and a numerical algorithm. In the next class, we'll study this algorithm. And this algorithm is called the coordinate ascent algorithm. It's called the coordinate. It's somewhat similar to EM, but little more generalized. It's called the coordinate EM algorithm. And it actually works when there are some restrictions on Q, on script Q rather. There are some script Q is of a particular type, and that particular type is called an mean field script, mean field Q, or something called mean field assumption about Q. If that holds, just like naive Bayes, it's a mean. It's very similar to naive Bayes. It's a mean field assumption on Q. If that holds, then this coordinate ascent method it works for maximizing the elbow. Okay, we'll study that in the next class. Thank you. Any questions? Okay, if there are no questions, let me stop the recording.